Good morning. We will continue with PCA and today we will discuss PCA model adequacy and interpretation. So, last class we have discussed up to extraction of PCA, extraction of principal component, and we have seen that first we have used S minus lambda determinant equal to 0, then we got the eigenvalues, and then using individual, suppose for the first one A1, first eigenvalue with the first eigenvector we have found out and subject to A1 transpose A1 equal to 1. So, similarly you can find out A2 using S minus lambda 2 I A2 equal to 0 and A2 transpose A2 equal to 1. In this same manner you will be able to find out the eigenvectors. Once you estimate the eigenvalues and eigenvectors, you can write down the equations also. For example, the example we have considered here, that the loadings we are calculating from profit and sales are the two variables, interrelated variables, and we have extracted also two component PC1, PC2, and these are all Z1, Z2, and the loadings, that basically this component loading or the eigenvectors 0.19 and 0.98 for your first one, that your component 1, 0.19 x1, 0.98 x2, and similarly for Z2 it is 0.98 x1 minus 0.19 x2. You see ultimately what is happening here, just reverse, only one sign reversal is there. So, what I ask you that you please compute in detail using this matrix, S matrix like 1.15, 5.76 and 5.76, 29.54, you compute in detail and you come to up to this level, you will be able to find out why, what is the reason of this type of relationships. Now, under adequacy test, what we want to discuss first, we have identified lambda 1, I think it is 30 point something, 666 probably 66, and lambda 2 is 0.03. Okay. Then the total is sum total of lambda j equal to 1 to 2 here, this equal to 30.69. Now, we have extracted this from this S matrix. Now, what is the stress of S? Stress of S is the sum total of the diagonal elements. This is 1.15 into 29.54 is not, this is 30.69. This is 30.69. Okay. Now, if S is P cross P matrix, then you will be getting like this. Suppose we are using sample S11, S22 like this SPP. Other way you can write S11 equal to S1 square, S2 square like this SP square, that you will be getting, and definitely there are off diagonal values are also there. But stress is this. So, I can say stress of S is nothing but sum total j equal to 1 to p is j square. Okay. So, this can be proved that your sum total of lambda j equal to 1 to p equal to sum total of j square. Sum total of, that means the variability, if you extract the maximum number of eigenvalues, and then what you will find out that sum total of this eigenvalues will be sum total of the variance component of the original matrix S matrix what you have considered. Okay. And you have already also found out one another thing. Suppose I said that variance of A j transpose x, this one also we found out that A j transpose S A j. So, now if I want to know what is the variance of Z1, that will be variance of A1 transpose x, which is A1 transpose S A1. It should be lambda 1. It will be lambda 1. How? What is your A1? In this case, A1 is 0.19, 0.98, S is 1.15, 5.76, then 5.76 and your 29.54. So, just you do this multiplication and find out, that is A1 transpose S A1. You find out, because this one you see A1 transpose is 1 cross 2, 2 cross 2, 2 cross 1. So, resultant will be 1 cross 1 and definitely this will be 30.66, which is
S A1 is lambda A1, and if we can take lambda, since lambda 1 is a scalar, we can take lambda outside and A1.
That you can do also, that is also possible. Basically what I am saying, suppose if you create a diagonal matrix of lambda, that is lambda 1 all 0, lambda 2, then lambda p, then what you can write basically sum total of this one, I think that is j square, j equal to 1 to p s j square, that you can write trace of your lambda A lambda, I think A transpose, that you can be it can be written like this. Now, you will what you will do basically, you why I am using A, because we have started with this, and then lambda, this is the transformation matrix. So, it will be lambda transpose your A, trace of this. Now, A transpose A, this is orthogonal I. So, trace of lambda into I, this will be trace of lambda, that means diagonal elements. So, sum total of j equal to 1 to p lambda j square. So, this is what is the decomposition. Lambda j square, j equal to 1 to p equal to s j square.
It's not square, I think.
Lambda j. Lambda j. If you go for singular value decomposition, then that will be that square will be there. Okay, fine. So, this is the case. So, I think you now understand that the relationships, everything is these are known. What is next? Next is, as I was telling you, suppose you got lambda 1 equal to 30.66, lambda 2 equal to 0.03. These are point estimates. because we have taken a sample S, that 2 by 2 matrix from n equal to certain values. I think our case n equal to 12, 2 variables values here. Suppose if I go for next time, as I told you earlier also. So, point estimate if you want to find out, then we are going for expected value of lambda j, let it is the theta j. That means, we are saying that in the population principal component, if you analysis if you do, there you will be getting the, if you know the everything about the population, you will be getting the exact value of that eigenvalue for that particular population. This is coming from sample, this is from population. So, this is one. Second is covariance of lambda j, lambda k, this will be 2 theta j square by n minus 1 for j equal to k and 0 for j not equal to k. So, this is the development. So, what I mean to say here then, that means the two lambda components lambda j and lambda k, they are variably when k j equal to k, this is nothing but the variance component, and that when j not equal to k, that is the covariance component. So, covariance is 0, variance is 2 theta j square by like this. Now, we can assume that this will follow a normal distribution with theta j and 2 theta j square by 2 theta j square by n minus 1. If you when that means you know the distribution. Now, how this distribution is coming, that is definitely a question, but it is a complicated issue. So, there are several researchers, statisticians developed this. So, we are sticking to this, that this means lambda j can be approximated to normal distribution, and provided definitely n is large, provided n is large. Now, when this is the situation, can you not find out the your that confidence interval for theta j? So, what we will do basically, you want to find out this minus z alpha by 2 plus z alpha by 2. We know that lambda j minus expected value of lambda j by standard error of lambda j, this follows Z01, that basic statistics, that concept. So, that means lambda j minus theta j. Now, what is the standard error of lambda j? Now, what is the value here? That variance part 2 theta j square by n minus 1. So, that means standard error, if you write down here, this will be 2 theta j square by n minus 1. Now, this quantity will be this side minus z alpha by 2, this side plus z alpha by 2. Okay. So, ultimately this one can be written like this, z alpha by 2 less than lambda j minus theta j by theta j will come out root over 2 by n minus 1 less than z alpha by 2. You do now mathematical manipulation, then ultimately what you will get, you want something like this, getting me. So, theta j will come out here, then this theta j is there. So, this theta j plus this quantity will be added, and then as it is within this, so 1 by something will come. Final form will be like this, 1 plus z alpha by 2 by n minus 1, then 1 by 1 minus z alpha by 2 by n minus 1, but we have this lambda j component. So, it will be lambda j, into lambda j you can write. Correct. If our alpha value is 0.05, then alpha by 2 will be 0.025, then z alpha by 2, this will be 1.96. Now, we got 30, our lambda 1 value is 30.66 divided by 1 plus 1.96 into 2 by 11, n is 12, less than equal to, also you can write this way, we write less than equal to 30.66 divided by 1 minus 1.96, 2 by 11. Okay. So, ultimately this quantity will yield that 30.66 by 1.836 less than equal to theta j less than equal to 30.66 by your 1 minus this 0.0164, and this leads to 16.70 less than theta 1, because we are considering j equal to 1. So, if I write theta j also j equal to 1 here, then this value is 186.95. But do you agree this? Do you agree with this? The reason is your original, see, your original data, sample data, if you see that the total is I think 30.69, this is the total variability. Now, if the see range is very high, it is because of many things, your number of variables is not, number of observation is very small. So, this is a huge difference. So, that means sticking to that first one, point estimate one only, that point estimate will okay, it is okay, all practical purposes it will serve the what you want to do, but see that this much variability for the population PCA is there, if I go by this simple sample PCA.
When n is very large,
Then this is true, then this
true result will
true reality, because we are saying that this is possible when n is large. When we are assuming normal distribution, when n is large, our case n is very small value. So, we cannot say that this is correct, but this is the way you will be finding out the confidence interval for the population eigenvalue. Okay. Now, another one is that you also similarly using S, that we found out that Aj, what is this, Zj equal to Aj transpose X. Now, this Aj you have found out the value of Aj, but this that is sample Aj. Correspondingly in population, suppose this is lambda j is there, that is this is the eigenvectors vector from sample, this is population eigenvector, jth eigenvector, population jth eigenvector. So, similarly there is definitely the distribution possible, but that distribution again really these are all complicated distribution. What it says that the eigenvector what you compute, this follows multivariate normal multivariate normal with Aj and Tj, where Tj is theta j by n minus 1 sum total of k equal to 1 to p and j not equal to k, theta k by theta k minus theta j square lambda k transpose, not lambda, that is alpha k transpose. This alpha is what? This one. Okay. So, as we are using here alpha k, okay, we are saying k equal to 1 to p, this type of big equation will come. Just for the sake of clarification, I request all of you to check this, that k and jth term, the notation, if there is, you just check this one. Okay. So, ultimately as we are getting that NP Aj Tj, that is the multivariate normal, you will be getting 100 into 1 minus alpha percent confidence region. Because it is p variable case, you will be getting the confidence region, and that confidence region takes this form n minus 1 alpha j transpose lambda j S inverse plus lambda j inverse S minus 2 I into lambda j, that follows chi square p minus 1 alpha. This is the confidence region. So, I am repeat that 1 n minus 1 alpha j transpose lambda j S inverse plus lambda j inverse S minus 2 I. This I is basically, if S is p cross p, then I is also p cross p, that is the identity matrix. Then this quantity will follow this distribution chi square p minus 1 with alpha. You can check this also, confidence region, all those things. And now, as it is confidence region, you may be interested to know the simultaneous confidence interval. Then you require to simplify it further. But these are really complex issues. But I am giving you basically what you have applied your PCA, that is from sample. Now, what is the guarantee that suppose in the texture direction what you are trying to find out, that you are actually going for the true, what is your sample size? It is quite large?
Yes.
Very large. Very large. So we are, I think you can still check the particularly the confidence interval for lambda j eigenvalues. That means the dispersion must be checked, and if it is very, I think it will be within the limit, because when n is large. Okay. So
each image of size 128 cross 128, then we have 128 into 128, this much data.
no, what is this 128?
128 into 128.
No, I understand, but 120, this is a matrix, 128 cross 128. What about n? What is n? Total observations.
Total is 128 into
128
128.
into 128. So these many observations are there. It's a quite large object. Okay. So I think that as you are doing it, maybe you will be we will be finding papers where this dispersion measures for the eigenvalues, that is not considered. That means uncertainty part is not considered. So you can propose, your adequacy will be much better. You can propose that okay, and maybe different sample size, how the adequacy, that your fitness will change, that can be also a good addition, theoretical contribution. Okay. Now let us see this, what is that example. Now see what happened, ultimately lambda 1 is this and ultimately this is what is our confidence region. and you have seen in multivariate normal distribution case the exponent term, that same thing it is basically. When I am talking about that that your AJ is multivariate normal, for two variable case the ellipse is formed, ellipse is formed. So, you find out the confidence ellipse for your eigenvector. Okay. Then I will show you the that model adequacy test in terms of Bartlett sphericity test. Then we will go for what are the different criteria that can be used to find out that what are the number of PCs that can be retained, and finally also we will show that some hypothesis test. What is this? Suppose what is happening? Suppose there are p x variables, you are extracting PCs, m PCs you are extracting. Let m is much less than p. For example, I am taking 20 variables and I then finally converting into two dimensional issue using PCA. So, that means you are excluding 18 dimensions, you are removing this. If your data is very highly correlated, then only it is possible. That means the 18 dimensions are not required, they are so much highly correlated that eigenvalues will be 0 for all the remaining 18s, only for 2 eigenvalues will be significant, others will be almost negligible. So, then that 18 PCs what you are not considering, are not they considering, are not they giving you something wrong signal that okay, if you go by subjective criteria of eliminating some of the principal components, it may give you some wrong results. So, finally, that is why what we want to say that some hypothesis test, that we are removing a subset of principal components, and then we want to see that whether those sets are contributing to the extraction or not, or to the explaining the variability. In true sense, that is not extraction. What I mean to say, that explaining the variability of the x, or whether the discarded components variability is very limited or small. Okay. What is Bartlett sphericity test? Bartlett sphericity test is very interesting. For example, you just see your data, scattered data x1 and x2, this is your data, this is random data. If you increase this, this is a random data set. That means there is no relation between x1 and x2. So, it resembles a circle. If I go for p greater than 2, that means p greater than equal to 3 or 3, what will happen? It will become a sphere. So, for this is for p equal to 2, it is a circle, for p greater than 3 it will be a sphere, greater than equal to 3 it will be sphere. Now, when you find out the circle or sphere, that means the variables are basically random in nature, variables are uncorrelated, observations scattered randomly without any systematic component. So, that means variables are uncorrelated. If each of the variables are uncorrelated with others, what will happen? How many PC component you can extract? Can we go for principal component analysis? For example, this is my case. Suppose if I rotate this, suppose this is Z1, this side it is Z2, are we gaining? No gain. Now, if I take the correlation matrix between these variables with no correlation between each other, what will happen? You will get only diagonal elements 1 and off diagonal elements all will be 0. So, if true sense the variables are not correlated, what is the meaning of going for principal component analysis? No need of diminishing. In that case R will be I. So, that is why what happened, that Bartlett's test is like this H0, that R is I, and a correlation coefficient is, that matrix is a identity matrix. Okay. Now, instead of this figure, if you get a figure like this, high correlation is there. So, in that case your this R, it cannot become, this cannot become 0, this will be having substantial value. So, Bartlett says then alternative hypothesis is R not equal to I, and he had developed the statistics value also. What is the statistics to be tested? The statistic to be tested is here minus n minus 1 minus 2p plus 5 by 6 log base A determinant of R. This is the statistic. Now, these statistics follows chi-square distribution with p into p minus 1 by 2 degrees of freedom. Okay. Sorry. Now, the example we have taken, there we have 12 observation, then we have 2 variables, then our log R, the determinant part, the determinant, if you see that determinant, that log R, that determinant of R, this one we have computed like this 0.258, the determinant of R. Okay. So, this quantity will become some value 9.5 into 3 point, that means almost 34.77. This quantity becomes 34.77. Okay. Now, what is your chi-square, that p means your 2 into 2 minus 1 divided by 2 into, let alpha is 0.05. So, this value will be chi-square 0.05. Okay. If you go, if you see the table, I think this value may be 0.0, very low value, not this much, 34 point, you will not get this. So, ultimately what will happen, your alpha value for this one is this value, and this 34 will be coming somewhere here. So, for our example, reject H0, R equal to I, and this is obvious, because if you see the R matrix here, this R matrix is 1, 987, 0.9871, this is the R matrix. I think similar, maybe 987 or something like this. Somewhere it is there. Okay. But very high value. So, when there is high value, that Bartlett's, this null hypothesis will be rejected. What we are saying, you can go for principal component analysis. Okay. Now, this is one of the tests. In fact, this test can be done much before the principal component analysis. You first see the correlation matrix, then this correlation, you go for Bartlett's test. If you find that yes, there is sphericity, no need of going for principal component. So much of effort, why should you put? So, then suppose okay, Bartlett's test rejected, H0 rejected, and you can go for several PCs. Now, what is the how many PCs you will keep? Number of PCs to be retained. There are several criteria. One of the criteria is cumulative percentage. Cumulative percentage variance explained. What we have seen? We have seen that the variance component of the original data matrix, that is equal to j equal to 1 to p lambda j, that we have proved. Okay. So, that is why what you do like this. Suppose your this is lambda j, that is lambda 1, lambda 2, so like this there will be lambda p. You find out the value of lambda 1 value how much, some value like this you are getting, then this is the value, then you find out cumulative value. Okay. For example, in this case our first one is 30.66, second one is 0.03. So, this is 30.66, this is 30.69. If I see the percentage, cumulative 36.55 by 36.69, this will be almost 99%.
30.66 by total sum of lambda, I think.
Yeah, that is the total sum of lambda, because we have only two for the example, that is 2. So, that is why this into 100 it will be almost 99%. Now, the thing is that you just go on doing like this, that lambda 1 divided by sum of lambda j, that lambda 1 plus lambda 2 divided by sum of lambda j. So, into 100 into 100. So, similar way then you find out what is the percentage, what percentage, like this. Then you put a cutoff, let my cutoff is 90%. So, those many lambda components you keep, that is cumulative percentage of total variance explained. This is what is the first criteria you can do. Okay. So, in this criteria what will happen, you may find out that in order to go for 90% of the total variability of x to be explained, you may take some of the principal components, for example, j plus 1 2 maybe j plus m, these many component, or up to j plus 1 to lambda p, these many components. These components you have taken, or if I say m, no problem, m, these components you have taken whose values are almost equal, very negligible. For example, if I plot like this, this is my lambda value, this side the PC values, PC1 to PCP component, you may find out first lambda value is here, second lambda value is here, third lambda value is here, fourth lambda value may be here, like this. You may get a figure like this. Actually, suppose 90% is coming here. This is your 90%, because if you go for cumulative at this point, if you extract here and you make a percentage column also, cumulative percentage, this will be 90%. Okay. So, but see, from contribution point of view, if I see, I think from here up to here it is okay, there is difference, but all those values are not significantly different. There is minuscule contribution, still they are there, because I want this. So, in that case you may not be interested in 90% total variability explained, you may sacrifice little bit, and then you come to some other total variability, maybe it is 80%, fine. So, then fine, you go for 80% and then this many component you keep. So, there are some other methods just to do this one, how nicely you will be able to do this. That is, another method is average root. Average root basically, what will be your average root? Lambda average 1 by p sum total j equal to 1 to p lambda j. So, you keep those many principal component whose value is greater than lambda bar. Getting? That means I have okay, so many components, you have a p component you have extracted, find out the lambda bar, then component 1 2 like this p component, and you check, suppose k components are having value which is greater than lambda bar, these many will be kept. Understood? There is another method known as Kaiser rule. Kaiser rule says that you, instead of S, you use correlation matrix, R matrix, that is the correlation matrix for extracting PCH. Okay. So, your correlation matrix is like this, all diagonal elements will be 1 and off diagonals values will be there, some values will be there. Then what is the trace of R? This will be, if it is P cross P matrix, that will be P. So, if I use correlation matrix instead of covariance, my total variability is number of variables. Correct. Now, what is the each variable variability in terms of when you go for standardized variables? When you are using correlation matrix, what actually you are doing? Instead of xij, you are transforming this xij to xij minus xj bar by sjj square root. Then if you compute S covariance matrix for this will be equal to R. So, standardized variable when you are taking, for every standardized variable mean is 0 and standard deviation is 1, mean variance is 1. So, now in this case what will happen, for every variable the variability of xj, that is 1. For standardization I am giving the tilde symbol. So, if any of the lambda j that is obtained from that correlation matrix value is less than 1, no need of keeping this, because this component is not able to explain a single variable variability. So, that is why what he says that you keep those principal component whose lambda value is greater than equal to 1. This is keep those many. Okay. So, there is another criteria which is, please.
I have one question regarding average root.
This one.
Yes, sir. Here we are arranging lambdas in descending order, suppose.
No, when you extract, your lambda 1 is always greater than equal to lambda 2.
Yes, yes.
You are getting me?
So, we are arranging eigenvalues in descending order.
That is what, it is obvious.
Yes.
It is obvious because your
Now,
this
lambda 1 must be greater than the average lambda.
has to be.
It has to be. So, one component is sufficient according to that criteria.
No, that is not the criteria. You take all those components whose lambda value is greater than lambda bar.
Okay.
Not one, not one. Getting me? It is not all the components having eigenvalue greater than the average eigenvalue.
Okay.
Okay. The another criteria is broken stick method. Here this combination is, first you find out a quantity called Lj, which is 1 by p sum total k equal to j 2 p 1 by k. Okay. This quantity basically it is just like a stick, if you broken into several component, that it is randomly that all the components any size you can get. So, that is why this type of 1 by k these things are coming. Now, your lambda j, okay, the cumulative value for each lambda j you find out. So, that cumulative value is lambda j by sum total of lambda j equal to 1 to p. You keep those lambda j whose value is greater than Lj. So, again the descending order is there, na, lambda 1 lambda 2 like this. So, you find out, so for the first one k equal to 1 to p, find out this quantity is this quantity is less than the cumulative percentage explained here, then keep this. Similarly, keep this. When you are going forward, ultimately k is changing. If it is first one is 1, second one is 2. So, from 2 to p 1 by k, that way you are taking the broken stick method. So, this is another criteria. Then the popular criteria, one more popular criteria is there, that is Scree plot. Getting me? Now, see the Scree plot here. Scree plot is nothing but you just this side you keep the lambda value, this side the PC, then put for every lambda values you put here, and you will find out that ultimately it will create, the curve will create an elbow type of shape. Elbow will be there. Elbow is the point. What does it mean? If you take the normal posture, the standard normal posture, sitting posture, in that case what will happen, your that forearm will be and upper arm should make 90-degree angle perpendicular, that is the thing. So, that means this elbow point you find out the point where this type of 90-degree you will not get here, but if you get, that is the best one. So, you are finding out where this elbow lies. You take principal number of component up to that elbow level. Okay, this is the visual one. The reason is, if I say my elbow and then this is parallel, all other, this is perpendicular parallel to horizontal, my forearm, that means other point here they are equally contributing, there is no improvement in terms of addition of some other principal component. Then you have to add everyone, all the things, because they are parallel. Okay. Now, in our case, this is 2 variable case only. So, 2 principal component, you have found out that only 1 component is enough, we do not require more. Okay. ठीक. Any question here up to this?
What we should study for all those analysis?
Which one you want to follow?
Yes.
And so many things are there. See, ultimately what happened, I can say that each are basically almost the same thing they are talking about, one way or other with a little difference. Now, cumulative percentage,
We have used that.
that is probably that we cannot ignore that one, because ultimately the original data set, this has certain variability, that covariance structure is there. What you are doing using PCA, that covariance structure you want to explain in some transform dimensions, some transform variables. So, if I am not able to explain that majority of the variability present in the original data set, then I think it is not a good model. So, cumulative percentage, where that is the first one we have to look into that, and then you have to think that what is the total variability that you must explain, the percentage of total variability that you must explain. In many situations you will find out that it is very difficult to explain even 50% of the variability. Now, question is, then if I require 20 variables, 20 dimension to explain 90% variability. Now, if I reduce it to 5 dimension and able to explain 80% variability, then definitely I will go for the 5 dimension with reduction of 20% variability. You are not able to explain the 25% variability, that 90 to 80, that is 10% reduction is there, correct, that is possible. Second thing, then why all those things are there, these are all basically you go for everyone, then you see which one is favoring you. But whatever you will do, either broken stick or Kaiser rule or your Scree plot, finally you have to see that how much the total variability you are able to explain. This Scree plot is basically a visual representation, getting me. And question is that, another important question is that whether we will go for S or R, which matrix you will explain. See, if you use S and if you use R, that you will get different results. It is in the transformed case. Now, it all depends on that what you want. You want that, suppose you are measuring the variables in different units, the variability is wide. Under this case, suppose your interest is not the strength, the pattern of relationship, covariance relationship, then I will ask you go for correlation matrix. Okay. That means whatever axis dimensions you get, it in terms of correlation matrix, that vectors, eigenvectors will be created, and there the pattern of relationship is more important, not the strength. If it is the strength is also equally important, then you go for covariance matrix, because covariance is in the original domain, not transforming. When you are going for R, you are going to the standardized variables. So, that you have to look into where you want to do. Okay. Then final one is that, as I told you, the hypothesis test, that Bartlett 1950 developed this one. So, suppose by these traditional method like Scree plot, broken sticks and other things, you are keeping out of p components, you are keeping m components, or let p minus m components you are keeping. That means m component you are discarding. Now, my question is, I want to test the m component collectively, what is contributing in explaining the variability of the original data matrix significantly. In that case, our hypothesis is that lambda m plus 1 equal to lambda m plus 2 equal to lambda mp, means the Scree plot you make, the Scree plot is horizontal. Okay, that is what you are trying to test. Then you are saying no, they are not equal for at least one pair. Then the hypothesis, the statistics is d equal to n p minus m log lambda m bar, and where lambda m bar is this one, because the component you are discarding, average of that. Then this quantity will follow chi-square distribution with these degrees of freedom. And then you know that chi-square table you have to follow, find out this value, and then you go for you change accordingly, you take your decision.
We should accept all lambdas whichever greater than lambda m bar.
greater than lambda m bar, but not that way straightforward here. What it is saying that if actual thing is that if they are equal, then lambda m bar will be individual lambdas. So, then using this, but you will in sample you will not get exactly the same value, there will be little bit of difference. So, if I assume that lambda, suppose lambda m is lambda j plus 1 or m plus 1 is greater than lambda m bar, and you will take this, then you are going by point estimate. What it is saying, no, you just see that there is a difference, whether that difference is significant or not. If that lambda m plus 1 minus lambda m bar is significantly different, then you keep, otherwise you do not keep, you say okay, that can be discarded. So, that is why the sample, this distribution is very, very important, and using this distribution you are first finding out the statistics, then you are finding out the value of the statistic, then you know that what is the chi-square degrees of freedom, and you go to table, find out this value. If you find that d value is greater than this, then you reject null hypothesis H0. What is this? All the lambda values are, the discarded lambda values are equal. Okay, so these many tests are there, and I think we should, nothing problematic, these are all simple to calculate, although very difficult to derive. For example, Bartlett, this test, all derivations are difficult, but very simple to calculate from the application point of view. You see all those things. When we come to this multivariate domain, what will happen ultimately, that you will find out that a large number of statistics are used to test the same thing. Now, what is the reason? The reason is all those statistics are based on certain assumptions. Now, and there will be deviation from reality. In raw data, when you collect the data, you will not find that they are actually following the assumptions of the statistics or the models you are using. So, you use several such statistics and you see that all are favoring or some or majority favoring or not. If majority favors to H0, go for H0, otherwise do not go for H0. Yes, Rahul, any question? Tanmay? So, I think we will stop here, and afternoon I will show you in Minitab or SPSS somewhere that given data how to go for your multiple regression, multivariate regression, then principal component analysis, and also we will see MANOVA part. Very simple, add data, things will, and click business, things will be done. Even then, once I show, it will be easy for you to use the softwares. Okay, thank you very much.